Can celestial bodies grow infinitely large? Could a single star ever match the size of the Milky Way? Earth is the biggest object visible to the naked eye, yet it appears tiny next to other celestial bodies in the universe. Jupiter, the solar system's largest planet, has a radius 11 times and a mass 3.17 times that of Earth. It is a gas giant. Its internal makeup is like the Sun's, but because it's less massive, its core forms liquid metallic hydrogen under gravity and can't start nuclear fusion. So, how big does Jupiter need to be become a star? Let's see. If you keep adding more Jupiters to it, its internal density will rise, but its volume won't grow significantly. With around 80 Jupiters added, the core pressure will start to allow intermittent fusion reactions, emitting a faint glow. However, at this stage, it is not a star. Instead, it turns into a brown dwarf, a body between a planet and a star, as its mass isn't enough to maintain the pressure required for nuclear fusion. To transform into a star, you must add more Jupiters. With around 100 Jupiters, the core pressure and temperature rise enough for hydrogen to fuse into helium, releasing immense energy and forming a red dwarf, the smallest type of star. Red dwarfs are the most common stars in the universe. If you add 900 more Jupiters to a red dwarf, you get our Sun. For a star the size of the Sun, even slight changes in size can significantly affect its brightness. For instance, Sirius, one of the night sky's brightest stars, is crucial after the Sun. Astronomers use it to set the standard for measuring stellar brightness, to measure the brightness of other stars. Despite being only twice the Sun's diameter, it shines 40 times brighter. Its surface temperature hits 10,000 degrees Celsius. But Sirius isn't the largest star out there. The heaviest known star is our 136A1. Its diameter is 30 times the Sun's, its mass is 315 times greater, and it shines 9 million times brighter. Theoretically, a normal star can't surpass our 136A1 in size because any larger star would experience such intense nuclear fusion that the radiation pressure would far exceed its own gravity, causing it to explode. This is known as the Eddington limit. Actually, our 136A1 continuously sheds material through stellar winds driven by radiation pressure, losing 3.21 million tons of mass every second. Normal stars can't surpass the Eddington limit, but dying stars aren't restricted by it. In 5 to 7.5 billion years, the Sun's hydrogen will slowly run out, transforming it into a red giant with a diameter 256 times larger. In the solar system, the Sun's volume is relatively small, but as a red giant, it will be large enough to engulf Earth. If a star larger than the Sun dies, it may evolve into a supergiant. The largest supergiant observed by humans so far is Stephenson 2-18. Its radius is 2,150 times the Sun's, and it shines 430,000 times brighter, filling Saturn's entire orbit. Even at the speed of light, it would take 9 hours to circle it, whereas it only takes 14.5 seconds to circle the Sun. But even supergiants have limits. They follow physical laws and will collapse or explode if they get too big. Yet, one type of celestial body can expand without limit: black holes. TON 618 is the largest black hole we've observed. Light takes a week to travel from its event horizon to the singularity. It can accommodate 11 solar systems side by side. Eventually, all matter will be drawn into a massive black hole, making it the largest star in the universe. In fact, every atom in our bodies comes from an exploded star. The atoms in your left hand might come from a different star than those in your right hand. So, in a strict sense, you were once a star in someone else's eyes.